Hello, everyone. Welcome to the ninth episode of the Scientific Saturday Lecture Series. These lectures are our endeavor to take global science to the students residing even in the remotest corner of the nation. I'm Vishaka Ranjan, founder of Gurukul Academy, and our guest for today is none other than Professor Jocelyn Bell Burnell. She inadvertently discovered pulsars as a graduate student, opening up a new branch of astrophysics. She has subsequently worked in many roles and branches of astronomy, working part time while raising a family. She is now a visiting academic professor in Oxford and the Chancellor of the University of Dundee, Scotland. She has also been president of the UK Royal Astronomical Society. In 2008, became the first female president of the Institute of Physics for the UK and Ireland. And in 2014, the first female president of the Royal Society of Edinburgh. She has received many honors, including a $3 million breakthrough prize in fundamental physics in 2018. The public appreciation and understanding of science have always been important to her, and she is very much in demand as a speaker and broadcaster. In her spare time, she enjoys gardening and choral music. We welcome you, ma'am.
Hello everyone, I'm Rishabh Nakra, founder and admin of The Secrets of the Universe. Before we invite Professor Jocelyn Bell Burnell for her lecture, I would like to remind everyone that we'll be taking questions after the presentation. So please post your queries in the comment section and we'll be taking it once the lecture is over. We welcome you, ma'am. We are very fortunate and privileged to have you with us today. Without further ado, we request Professor Jocelyn Bell Burnell to begin the session.
Thank you both, and thank you to my audience for your patience. So I want to tell a story of what happened to me when I was a graduate student. So this will be under the heading of Reflections on the Discovery of Pulsars, because it is now many decades ago that this happened. Thank you. Could I have the next slide, please? Aha, how do I? Yeah, right. So I'm going to tell you the story of how pulsars were discovered. I'll also, if I have time, tell you some stories about how pulsars were nearly discovered before I discovered them, some near misses, and then maybe some reflections if we have time. And then the next slide. So I had most of my education in the north and west of the British Isles. Cambridge is in the south and east of the British Isles, and it felt like an alien country when I got there. Furthermore, on the second day, I was given this set of tools. This sends a message about what kind of work I will be doing as a PhD student. These are not microelectronics tools. These are full-size wire working tools. Thank you. Next one. This is a photograph taken about 2 years later. We're working in the field, as they say. We've been building, building a radio telescope, and it has involved quite a lot of outdoor work. So I'm sitting on the right, and my technician Don is on the left, and we're checking the impedance of some very special cables that you could not coil up and take indoors. So I had to work out of doors. The antenna is nearly finished now. It's a very large one, working at 81.5 megahertz. If we go to the next slide, please. This is a picture of the antenna. What you see are lots of wooden posts. Their job is to keep the bare wires up clear of wet grass. And you can see quite a lot of copper wire because it's oxidized. It's that nice blue color. This is an array that covers the area of 57 tennis courts, had about 2,000 antennae in it, worked as an interferometer. And way back then, we were not using transistors. We were using vacuum tubes or valves. Thank you. And the next slide, please. Now, the purpose of this project and this antenna was to discover more quasars, more quasi-stellar radio sources. At that stage, there were about 20 known, and they were clearly very interesting, very exciting objects. They were extremely distant and yet also extremely bright, which was a bit of a puzzle. They were very compact, very small angular diameter. And because they were small angular diameter, they would change their brightness, they would scintillate, they would fluctuate in brightness as the signal from them came through the space between the sun and the planets, which wasn't actually space, empty space, it was full of solar wind. And the solar wind is not smooth, it has clouds of higher electron density in it. And these clouds act like a diffraction screen. In fact, they act like a moving diffraction screen. And so we see the quasar apparently changing in brightness, like you see in the bottom part of the slide. It changes very quickly, so you have to have a short integration time in order to see these changes. Radio galaxies are much more extended and have a much steadier, they're seen as a much steadier signal. They don't fluctuate. So a good way of picking out quasars is to look for these sources that fluctuate. And that was the purpose of the whole exercise, to find more quasars. And I have to say it worked. I started with about 20 quasars, and by the time I had finished, we had about 200. So that was a good size of sample. But we had something else as well, as you probably know. The next slide, please. So what we do is we repeatedly survey the sky. We survey the sky with a very fast integration time, short integration time, and we look for things that change their brightness. Those are quasars. Things that do not change their brightness are radio galaxies, and we're not too worried about those. It took 2 years to build the antenna. There were about 6 of us working on it. And when it was built, the other 5 moved on to other jobs, and I was left to operate the telescope and analyze the data. The data came out on paper chart. The next slide, please. So the paper chart, like you see in this slide, contains my data. The university did have a computer at that stage, one computer. It occupied a whole room, and it had memory comparable to the memory of your laptop. It's not made of transistors, it was made with vacuum tubes, which is why it was so big. And very few people could have time on it. And we didn't. So no computer. The data came out on these paper charts. There was 30 meters of these paper charts every day. And I observed for 6 months, so I had over 5 kilometers of that paper chart, which I analyzed very carefully, very thoroughly. Thank you. The next slide. Now, I got used to identifying quasars. I also got used to identifying man-made interference created by human beings. Maybe there was somebody driving down the road in a car that was badly suppressed. That could give a radio signal. Maybe somebody was using an arc welder. Maybe there was aircraft altimeters, taxi radios, all sorts of things could give interference. There are bands that are kept clear for radio astronomy so that we can see the signals from space, but sometimes other signals stray into those bands. And indeed, we had trouble from a pirate radio station who noticed this clear band and decided it would broadcast there. So until that pirate station got shut down, we didn't get much astronomy done. I quickly got used to identifying the twinkling quasars, which is what I was meant to be doing. But just occasionally, there'd be about half a centimetre in the 120 metres of chart paper per scan that showed an unusual signal. And I have an example of it here. There's a band across the middle of the signal. A lot of it is just static. There's one lot labelled interference, and there's another lot labelled CP1919. That, in fact, is the first pulsar, and it looks different from the interference signal. With the interference signal, the spikes go up and down, whereas this curious signal to the left, the pulses go mainly up, the spikes go mainly up. In the interference signal, you can see chart paper between the spikes, whereas with this curious signal, there's certainly a chunk where they're so close packed you cannot see chart between the spikes. They look different. And actually, when you say they look different, what you are doing is a Fourier analysis. When we say we can see chart paper between the spikes, or we cannot see chart paper, we're talking about the frequencies. The interference signal has lower frequency, so there's chart showing between the spikes. The interference signal, the spikes go up and down. With what turned out to be a pulsar signal, they go mainly up. So that's talking about the pulse amplitudes. So by comparing the pulse frequencies and the pulse amplitudes, or actually doing a Fourier analysis, we say that this unusual signal on the left looks different, must be different. I showed this to my thesis advisor and he rightly observed, look, Jocelyn, that occupies 5 millimeters. We can't see what's going on. We need an enlargement. And with chart recorders, paper chart recorders, an enlargement is quite easy. You run the paper faster under the pen and the whole thing gets spread out. The snag is we couldn't leave the pen recorder running at that rate all the time, or it would have run out of chart paper, got through the whole roll of paper in 20 minutes. So the graduate student, me, has to go out to the observatory shortly before this bit of sky is due to be observed, switch to high-speed recording, let it run for 10, 15 minutes, and then switch back to normal. And I did that for weeks and, well, about a month, and nothing happened. It had disappeared. I was making high-speed recordings of receiver noise. And my thesis advisor was getting very cross. I'd missed it, and it was all my fault. And then one day, something different happened. Could I have the next slide, please? So we've got 3 traces here. Concentrate on the bottom 2 for the moment. The very bottom one is a time signal, 1 second time pips. Each of those peaks, downward going peaks, are 1 second apart. The middle trace, labelled LGM1, is the signal that I managed to pick up. And you can see across the middle stretch of it that it's a string of pulses. They've got different heights, but they're equally spaced, allowing for some that are completely missing. And by comparing it with the 1 second time pips in the bottom trace, you can see that the spacing is about 1 1/3 seconds. We also happen to have on this slide the tracing of the third pulsar I discovered, which has a rather different period, as you can see. LGM stands for Little Green Men. It was the nickname I gave these things. It was only a nickname. I did not really believe it was Little Green Men, especially once I found more than one, but the name stuck. So Little Green Men. And a pulse rate of 1 1/3 seconds is alarmingly fast because astronomical objects are big things, and big things turn slowly. Think of comparing how a bicycle turns with how a bus turns. The bicycle can turn sharper than the bus. So these things pulsing rather fast must be rather tiny. But stars are big things, they're not tiny. What's going on? Is it interference? Am I picking up some other kind of radio signal? Could we have the next slide, please? Thank you. So my supervisor's first thought was, okay, it's radio interference. But I knew it wasn't because I'd been tracking this for quite a few months. And I knew that it kept to the sidereal day, the 23-hour, 56-minute day that the stars keep to. You'll be aware that what you see in the sky in wintertime is different to what you see in the sky summertime. There are different constellations. That's because the stars go round in 23 hours, 56 minutes. The stars get 4 minutes earlier every day. This thing, whatever it was getting 4 minutes earlier every day, very reliably. But maybe there's a fault with the telescope. Jocelyn's done the wiring. Maybe Jocelyn has wired it up incorrectly. So we asked a colleague and his graduate student who also had a radio telescope, a separate one, completely separate, on the same observatory site, but with its own receivers and everything. We took them into our confidence and said, look, don't broadcast this, but we've got a funny signal. We're not quite sure if it's real or if it's a fault with the equipment. Would you look with your equipment to see if you can see it? And they could. They did, after a false start, which gave me some bad moments. But they did pick it up. So it's not a fault of our equipment. I have not wired the radio telescope up wrong. It's beyond both our telescopes. But the two telescopes are fairly close together, a few hundred meters apart. So maybe it's some sort of interference. And we tried to work out what it could be and weren't having great progress. The other big problem with this source was the thing had to be small because the pulses were short and steep. But we already were seeing that the pulse period was not changing. We were measuring it to 5 decimal places, 6 decimal places, 7 decimal places, 8 decimal places before we saw any sign of change. If something's going to keep pulsing reliably at the same period, it's got to have big reserves of energy. So it's got to be big. But the pulses are short and steep, which means the thing is small. So it's small and it's big, which doesn't seem to make sense. This is the nature of research. You sometimes hit conundrums and you just can't see what's going on. The next slide, please. A colleague managed to get an estimate of the dispersion. As a radio signal travels through space, if there are any free electrons, and there usually are, the high frequencies will travel faster than the low frequencies. And the signal will come in first at the higher frequencies, followed later by the lower frequencies. And if you can measure the delay between the two frequencies, and make a guess at how many electrons there are out in space, because it's the electrons that cause this effect, then you can get an estimate of the distance. So we managed to do this. A colleague, John Pilkington, did it, and the estimate came out to be 200 light years away. So it's well beyond the sun and the planets and any satellites we've sent up. But in terms of the Milky Way, our galaxy, it's actually pretty close. Tony, in particular, my supervisor, was concerned that it might be little green men, a civilization signaling to us. And he argued that if it was little green men, they probably lived on a planet which went round their star. And as their planet goes round their star, some of the time it's moving away from us, and some of the time it's moving towards us, and we should see slight changes in the pulse period due to the Doppler effect. So Jocelyn, please keep continuing to observe this, get traces of these pulses as often as you can, and we'll measure the period. So I did this, but we couldn't find, well, I was going to say we couldn't find any Doppler effect. That's not strictly true. We couldn't find any Doppler effect due to the source. But those of you who are physics students will know that you can get Doppler effect by motion of the observer as well as motion of the source. And we, the observers, are on the Earth, and the Earth is moving round the sun. And in fact, we could see the change in the pulse period due to the motion of the Earth. So we proved that the Earth went round the sun, but otherwise weren't making a lot of progress. And then I found another one, and this was a huge relief to me. It was in a totally different part of the sky. It had a similar but different period. It was sufficiently different that we knew it was a distinct thing. And then I found a third and a fourth. And this now begins to look like a population of something. We still didn't know what these things were. We could say that they were small and they gave out pulses. And we could say that the Earth went round the sun. That was about where we were. Could I have the next slide, please? We duly wrote up the result in a paper published in Nature. It attracted a lot of attention. Tony gave a colloquium in Cambridge just before the paper was published, gave it a very titillating title, and everybody came. And most of them hadn't heard anything about this because we'd kept very quiet about it until we were sure we were not being stupid, that it really was real. I remember Professor Fred Hoyle came, sat in the front row. Tony gave the colloquium, and when he finished, Fred was the first to speak. At that particular point in time, Tony favoured an oscillating white dwarf model. White dwarfs were then the most compact stars known, and he imagined that the stars could be vibrating and launching shocks up into the atmosphere, which somehow gave these radio pulses. So Tony described his picture of an oscillating white dwarf. Fred Hoyle, as I said, was the first to speak, and he said he didn't think it was a white dwarf. He thought it was a neutron star. And I was amazed. He had not heard of these things until 40 minutes ago. And he's actually, in retrospect, hit the right explanation within 40 minutes. Well, the rest of us are trying to explain it as white dwarfs. When we published the paper in Nature, there was a lot of publicity around it and a lot of newspapers took an interest, and television and radio stations. And we did a lot of interviews. The interviews, I'm afraid, had a very standard format. They would ask Tony Hewish about the astrophysical significance of this discovery. And then they turned to me, the young woman, for what they called the human interest. How tall was I? What were my bust, waist, and hip measurements? How many boyfriends did I have? Would I describe my hair as brunette or blonde? And the photographers wanted me to undo more of the buttons on my blouse. It was horrible. But that's what young women were for, apparently. One of the journalists was rather more sensible. It was from the Daily Telegraph, Anthony Michaelis, and he asked us what we were going to call these things. And we'd given some thought to this, and we said pulsating radio stars. The other option was pulsed radio stars. And we thought pulsed maybe implies some agency, little green men making the pulses. Pulsating radio stars makes it sound a bit more natural. So he said, pulsating radio stars. And he said, no, short name. And he came up with the name pulsar by analogy with quasar. Thank you. Next slide, please. Now, one of the delightful things about having found pulsars is that in subsequent years, a number of people have come up to me and said, you know, I nearly discovered pulsars, and tells me the story of how they nearly discovered pulsars. So if the organizers are happy, I'll carry on and tell you some of these stories briefly about how pulsars were nearly discovered. Could we have the next slide, please? So this is 1957. We're in the United States at the McDonald Observatory in Texas. Mr. McDonald gave money for the observatory, for the telescope, but said that the observatory had to be open to the public one night per month. And this is the night that it's open to the public in this month. There's a young man, Elliot Moore, who's just finished a physics degree in Chicago University and is working at McDonald over the summer as an intern. And he's there that night and he tells this story. The telescope is set on the center of the Crab Nebula, where there's a rather curious star. We now know that this is the remains of the star that exploded to create the nebula. It was known as Minkowski's star. And members of the public step up to the telescope, look through it and say, oh, wonderful, fantastic, gee whiz, whatever they said in the United States in 1957. And a young woman steps up to the telescope and says, that star's flashing. And the night assistant starts to explain about how stars scintillate, twinkle. And she stops him. She says, no, I know about scintillation. I'm an airplane pilot. This is 1957. I'm an airplane pilot. My job is to fly airplanes from the place where they were built to the customer. I fly mainly at night. I know about scintillation. That star's flashing. Elliot Moore remembers the incident and says nobody followed up. It was said that they had no instrumentation to follow up. He thinks actually they just were more interested in pursuing their own topics, not following it up. And the next slide, please. Much later, around about 2007, the Australians who do a lot of pulsar research have made a catalogue of the pulsars known and put it online. And they get an email from a very excited elderly American called Charles Schisler. He says that back in the late 1960s, he was in the United States Air Force. He was posted to Alaska, where they had radar, which was looking out for incoming ballistic missiles from Russia. It's an early warning site. There aren't many missiles coming in from Russia. It's pretty quiet. He's allowed to play around with the kit, and he uses it to receive radio signals from stars and things in the sky. And he discovers 14 pulsing sources up in the sky. He's done an astronomy course when he was a student, and he remembers about right ascension and declination. And he makes a note of the right ascension and declination as best he could of these 14 pulsar signals, writes them on a bit of paper, and probably illegally keeps that bit of paper with him when he leaves the military. He's now just discovered the online pulsar catalogue. The next slide, please. The online pulsar catalogue has a number of his sources in it, and in particular, the crab. Move the next slide, please. So this is how he describes it. At the time, I carefully made notes and the approximate location by RA and DEC. 10 or 11 of them have been identified as being pulsars, as I've just discovered from the ATNF catalogue of 1771 pulsars. It's possible that all of them were pulsars. The first one that I discovered back in 1967 was the Crab Nebula, and may have been the first pulsar ever noted by anyone. I'm now 81 years old, but I'm still curious about a very exciting thing that happened to me 40 years ago. So it looks as if he discovered pulsars about the same time as I did, but he wasn't allowed to publish. He wasn't in a position to publish. Go to the next slide, please. The final example actually comes from the ultraviolet. No, this isn't. This is the last but one example, sorry. And it involves Sue Simpkin. Sue Simpkin was born in Canada. At one time in Canada, the mains electricity power supply was at 30 hertz. This was troublesome to some people because some people can see that frequency. Particularly, it turns out, young women. And Sue Simpkin was one of those young women. She said she was driven mad by all the lights and the television and everything flashing at 30 hertz. She knows she can see 30 hertz. And incidentally, remember that back at McDonald Observatory, it was a young woman who said the Crab pulsar was flashing. Crab goes at about 30 hertz, so I think it's very possible that she saw it as well. Anyway, Sue Simpkin has an ultraviolet spectrometer, and she's got time on the Kitt Peak telescope, and Lo Vulture, an eminent Dutch astronomer, asked her to take a spectrum of that funny star in the Crab Nebula, Minkowski's star. Sue observes it. She says the spectrum is pretty dull, but as she's observing, she sees a sort of flickering, or as if waves were going out from it. Lo Vulture says it couldn't be. But when the pulsar in the crab is discovered, he's man enough to say she probably saw it. She probably did. But she didn't publish, and it was only after the crab pulsar was identified that she started telling this story. And the next slide, please. So this is the final story about how pulsars were almost discovered. There's a group of radio astronomers making a map of the radio sky, the whole sky, at 408 megahertz. They're using large telescopes. They're getting time on large telescopes, a week here, 10 days there, 5 days on that one. And they've almost completed the map of the sky. There are just a few little patches to fill in. They believe they're in their last week of observing. This is also pre-computers. They're using pen recorders. And one of the pen recorders is misbehaving. It sticks and catches. It's not operating smoothly. In the early hours of the morning, 2 o'clock, 3 o'clock in the morning, which is quite the worst time of day to be awake and observing, that pen recorder starts going wheep, 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 wheep. And the observer says, damn. I'm not naming him, incidentally. He was always very embarrassed by this. The observer says, damn, and do what we always did to pen recorders, which is thump it. So he thumped it, and the pen recorder stopped sweeping across and went back to its normal behavior. He said, oh, good. Put on his coat and went home to bed. And he did not make any note in the logbook. If he had recorded that in the logbook, they could have claimed prior discovery of a pulsar, because we now know that they were observing a well-known pulsar. And that's why the pen recorder was sweeping backward. The pen was sweeping backwards and forwards. So this is why students are always told to make notes in their lab books of what happens. It applies not just when you're a student, but when you're a professional scientist as well. The observer was always very embarrassed about this. He's no longer with us, but I'm still not going to name him. Use your notebook, folks. Record it in the lab book. And the next slide, please. Yep, I think I've probably said all of that. It was the pulsar 0329 plus 54 that they were observing. It's quite high latitude. For those in the northern hemisphere, it's circumpolar. It does not set. Good, thank you. And the next slide, please. There was also something remarkable that happened that I want to tell you about. There was a very eminent, very clever Italian astrophysicist called Franco Pacini. It's a photograph of Franco. He died perhaps, 5 or 10 years ago. And he was wondering what kept the Crab Nebula shining. The Crab Nebula, we know, was a star that exploded in 1654 AD. It was observed by the ancient Chinese. There are records of its explosion. We can still see the nebula, the remains of that exploded star today. But why can we still see it? It really ought to have faded 300 or 400 years later. Why is it still shining brightly? And Franco wondered if the explosion of the star had created what's called a neutron star, which is what we now know pulsars are, a neutron star with a large magnetic field, which is what we know pulsars now are, and that the magnetic field axis is inclined to the spin axis, as we now know is the case with pulsars. And as that magnetic axis swept around, you get magnetic dipole rotation at the rotation period, and perhaps that cannot get out of the nebula. Perhaps the plasma prevents that signal, that frequency of signal getting out, and so the energy and momentum are dumped in the nebula and keep it shining. Franco was right on all those counts. The funny star in the center of the Crab Nebula, Minkowski's star, we now know is a neutron star with a large magnetic field inclined to the spin axis. And as it spins, it dumps energy in the nebula, which keeps energy and momentum, which keeps the nebula shining. Thank you. And the next slide, please. So I want to take just a couple of minutes, if I might, saying, why did the discovery happen when it happened, and where it happened, and how it happened? Because there had been all these 4 or 5 instances where pulsars were nearly discovered, but weren't. The next slide, please. First of all, we had our own telescope and receivers, and I made it my job to understand how they worked, what their foibles were, what their performance was. Also, as a research student, I had no other responsibilities, so I had time and space to follow up on anomalies. And because I was suffering from imposter syndrome, which I can explain later if people need an explanation, I was countering that imposter syndrome by being very, very thorough, pathetically thorough, careful. So I was following up every anomaly to make sure I understood how that telescope operated and why that anomaly was what it was like. Also, this particular project was one of the first instances where we'd used a short time constant, a short integration time. So to use more modern jargon, we were moving into a new area of phase space. And we reckoned we probably didn't have any competitors close on our heels, so we could take the time to make sure we really understood what was going on before we published. And the next slide, please. Being University of Cambridge, we had a reputable address. If you're going to discover something really very surprising, it does help if you're coming from a good address. People are less likely to think you're mad or have made a mistake. But one of the things that has happened subsequently in Britain and probably in other countries is that if you get money for research, you have to say what your objectives or targets of the research are, and then you write a report showing how you have achieved those targets or objectives. And this wasn't one of our targets or objectives. It couldn't have been because we didn't know they existed. It actually turned out to be far more important than the work we were meant to be doing. But would we have been marked down for taking away time from the program that we said we'd do? If we had been able to computerize the search, would we have bothered looking for anything like this? Would we have programmed the search to pick up anything like this? I think we would have been struggling because computers were so limited that we would have had to have focused on the real project, the scintillating quasars, and pulsars might not have been discovered. We also were working at lower frequencies than many people. There's still not so much low frequency work done. And up till then, time domain, things varying in time, hadn't really been studied at all in radio astronomy. Thank you. And the next slide, please. Thank you for your interest. Thank you for your attention. And I hand back now to the organizers.
Thank you so much, ma'am, for an interesting and insightful talk. I must admit that today's talk was just not about pulsars or radio astronomy. It was a story about compassion, kindness, elegance, personal values, perspective, and most importantly, giving back to society. You didn't even let the lack of recognition bog you down and continued working towards inspiring young minds. You are really a role model, and not only in science, but for humanity. And the best part about the presentation was that it highlights that scientific discoveries require a lot of patience, and the discovery of pulsars is the best example to support that. So now we'll be taking up some questions which people have posted in the comment section. And the first question is by Peter, and he's asking, what factors decide that a particular star will end up as a neutron star, a pulsar, or a magnetar after it dies?
Right. If a star is very large, when it runs out of fuel, it'll collapse to be a black hole. But if it's under about 2 times the mass of the sun, it's much more likely to collapse to a neutron star and not go the whole way down to a black hole. So it doesn't want to be too massive or it won't become a neutron star. Equally, it probably has to be over about 1.4 solar masses. So it's in a rather limited mass range, becomes a neutron star or a pulsar.
So, ma'am, what is the criteria that what decides that if it is if it will become a neutron star or a magnetar or a pulsar between these three?
Right. Well, magnetars and pulsars are both neutron stars. The difference between pulsars and magnetars is that magnetars have an even larger magnetic field and sometimes show some flaring behavior, whereas the pulsars don't. The pulsars just pulse.
Okay, thank you.
Thank you, ma'am. The next question is coming from Sarthak. He asked, what is the possibility of the existence of planets around pulsars?
We know of one or two cases where there are planets around pulsars. Given that a pulsar is created when a massive star goes supernova and explodes, the explosion can eject any planets that there were. But obviously, in a few cases, either the planets remain or they've been captured subsequently. So we know of just a few cases of pulsars with planets. Not many, but there are some. I don't think those planets would be inhabited because the radiation in the pulses that close to the pulsar would be lethal for anything live. So I think they're probably sterile planets, but there are a few cases of planets around pulsars.
Thank you so much, ma'am. It takes me to this, another question that, will be mine. That, these planets that you're talking about, habitation over there, and as you mentioned, the little green men. If the little green men are of the sizes of microorganisms, with and are are very intelligent also. So, do you think that the Voyager that has has that pulsar, the disk that has gone in the space, what happens if it reaches to them? If they are able to
Well,
find,
yes. Yeah, just
what will they think? Another asteroid, attack on them?
that plaque on the satellite tells people who can decode it where the satellites come from, where Earth is, and it's described its position in relation to a number of pulsars. And the pulsar period, the pulsar direction is given as a line radiating out, and the pulsar period is encoded in binary. So they have to be pretty intelligent, little green men, to work it all out. But if they do, they can work out where Earth is. They can incidentally also work out when that plaque was engraved, because pulsars are gradually slowing. So the periods that are given for those pulsars are faster than the periods now. And with a little bit of scientific ingenuity, the little green men who pick up that satellite could work out when the plaque was engraved, how long ago the plaque was engraved.
Thank you, ma'am.
Thank you, ma'am. And the next question is by Deepika. And she's asking, what do you think will be the next great discovery in astronomy?
Wow, there's a lot happening. One of the newest kinds of astronomy is gravitational wave astronomy, where we pick up what are loosely called ripples in space-time from colliding stars, black holes orbiting, this kind of thing. And this is a very new branch of astronomy and is proving very exciting, zooming ahead very, very fast with all sorts of unexpected things, like there are lots of black holes of mass about 30, 40, 50 times the mass of the sun, and they collide quite often, and that gives gravitational waves. which the gravitational wave detectors are picking up. Now, India is getting its own gravitational wave detector, so we'll be joining this game, I guess, in just a few years' time. So if any students were interested in going into that area, I would suggest it's great fun to be in early on a topic like gravitational radiation. And there'll also be a lot of important theoretical work to do. So, yeah, I've rambled a bit. There's a lot happening.
And do you think that pulsars will play a role in gravitational wave astronomy?
They play a bit of a role, but it's actually black holes that are dominating the field at the moment. Yes, they have picked up some neutron stars twinned with a black hole, and maybe even some neutron star pairs. I'm not absolutely certain about that. I think they might have. But it's actually black holes that are dominating the gravitational wave work at the moment.
Thank you so much, ma'am. So the next question is my question, which I personally wanted to ask you. You mentioned that the data was collected on a sheet of paper back then. And today, as the technology has evolved so much, and we are able to collect so much of data and store a large
Yes.
set of data, can you explain your experience? Because you have been you've witnessed this transitions and how it has helped you in the research. So can you explain your experience?
Yes, I'm aware, for instance, that there's a new telescope in Chile that will open fairly soon, the Vera Rubin telescope. It's going to look for flashing and bursting events. And the estimates of the number of events it will find per night are between 1 billion and 10 billion per night. No way can graduate students analyze that. It's going to have to be done by computer. And furthermore, the computer will then send out an alert to the computers at other telescopes all around the world, saying there's something happening on star blah, 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 blah. And then at that observatory, they can decide whether to go look at it or not. So a whole new domain happening. But that's the way science goes. New things open up. Pulsars will continue to be an interesting area of research. They are going to be important for studying a particular range of gravitational waves as well. So, yeah, important things, but there are other things happening as well now.
Thank you, ma'am.
Thank you, ma'am. And the next question is by Liv. And the question is astronomy a significantly more inviting field today for women than it was way back then?
Yes, undoubtedly, which is not to say it's perfect, but it's a lot better than when, some of us started. And there are a lot more women doing it. I don't know how it is in India, but in terms of Britain, you look at physics, you find that astronomy has probably the greatest fraction of women compared with all the other branches of physics. It's not to say the fraction is big enough yet, but it probably, of all the bits of physics, astrophysics probably has the most women.
Wow. Okay, ma'am. So the next question is from Ishita. She asks, who is or what has the greatest influence on your life?
Oh dear. I'm not sure that it's a person. I've really had to make my own way, to be honest. There have been very, very few women ahead of me. Some wonderful ones, but not many of them, to be honest. There are many more coming along behind, which is great. I'm not sure that I would point to a single person, to be honest.
Ma'am, any incident that you can recall, that the work that you're doing, any incident that is inspiring, or the way you are. Of course, there must be many incidents, I'm sure. that
Yes,
made you who you are today.
for quite a long time I was married, and my husband had to move to different parts of the country. So I moved with him and had an amazing variety of jobs in astronomy of one sort or another. And some of it's proved very, very exciting. I happened to be in X ray astronomy just as our lab launched an X ray astronomy satellite, which was hugely successful. And that was a very exciting time as well, because it kept discovering things, usually on a Friday afternoon, just when we want a weekend off. Oh, there's a new transient source. We'd better do something about it.
Okay. Thank you, ma'am. We'll move
Okay,
on to the
thank you,
next.
ma'am. The next question is, what is the relationship between strange quarks and pulsars?
I'm not sure that there is a relationship, to be sure, but the inside of a pulsar or a neutron star has some very extreme physics. It's got a solar mass, 10 to the power 30 kilograms, all in a bowl about 10 kilometers wide. It is extremely dense, and the physics of the interior of a neutron star is still not well understood and quite debated, and quarks will be part of that story, I expect. But it's still not settled. There's big arguments going on.
So there is probably no way to test the theories also, I guess, as of now.
Probably not at the moment. As the theories improve, they can be checked to see if they give sensible kinds of neutron stars, with a reasonable radius and a reasonable mass. But I don't think they're at that stage yet.
Okay,
Right.
ma'am. We'll be taking the last question, ma'am, because of the time duration that we have. It's coming from Sri Vintya. She asked, how do you exactly know that the signals are received from quasars? It could be other space objects. How do you filter it?
Um, there are several ways you can sort of check this out. As a pulse from a pulsar travels through space, it suffers dispersion. We've seen dispersion of light, light going through a prism splits into the rainbow. A multi-frequency signal from a pulsar coming through space. The different frequencies arrive at different times. The high frequencies first, and then lower and lower and lower frequencies. And you can see how fast that's dropping in frequency and see if it's plausible, sensible. What's causing this dispersion is free electrons in space. And although we don't know exactly how many electrons there are in space, if we come up with a number that's a factor of 100 too big or a factor of 100 too small, then we would doubt it. But it comes up with what we think is a sensible number. So there are some checks you can do, even though you're dealing with things way out in space.
Okay. So thank you so much, ma'am, for your time today. And on behalf of Gurukul Academy and Secrets of Universe, I once again extend my very hearty gratitude to Professor Jocelyn Bell Burnell for accepting the invitation and sharing with us your valuable thoughts. Your thoughts have enlightened our minds and have showed us a new path. I would also like to thank all of you for joining us from different parts of the world. It is your love and support that keeps us going and inspire us to continue our work. Stay tuned to our channel for many such talks on the coming Saturdays. And I would also like to thank Tanya, who is being, who's being with you and who helped a lot, for today's lecture. So thank you so much, Tanya. And ma'am, we'll